I'm going to record the class, okay? And if you don't see me doing it, you can remind me. And I will upload it in a YouTube channel. Okay, so make sure you take attendance here. You click on your name only once, okay? If you forget, you can do it after the class or during the class. As long as you don't, you go quietly, it's fine. So make sure you are in the right class. So it's physics without calculus, okay? So make sure it's the right class for you. So I'm going to introduce the class first. For those who were here last semester, it works the same. So that's going to be my grading scheme. So you see, homework will be 18% of the final grade. You have 2 attempts, and it's in Canvas, okay? So you take it online. I highly recommend that you try really hard first without looking at hints, because I will give you hints and sometimes you will have tutorials in my Dropbox. So first you do it try to do it on your own, and then you can look at the answers, okay? Because the goal is to really understand the material and prepare you for the test. Another thing that I highly recommend is to have a study group, not on WhatsApp, okay, but in person, a group that you can work together on the homework. Because, you know, some students will remember one thing, other students will remember another thing. Some students are good at conceptual questions, some other students will be good at numerical questions. So really, make friends, you know, say hi to your neighbor, okay? And make new friends. Because as we say, especially in the US, everything is connection, connection, connection. Okay, so that's the right time to make connections at physics class. And then for the test, yeah, you're gonna have 3 tests in person, on paper, in class. So that will be for test 1, test 2, and the final. The final is cumulative, and they already gave us a date, April 25th. Okay, I think that date will be okay. So each test here is 20%. And I'm going to try to do test 1 and test 2 at those dates here. It's a Tuesday. Okay, so usually tests are multiple choices, about 20 questions, and they count each for 20%. And then something very annoying, I have a pop quiz every lecture based on the previous lecture. Okay, but it's open notes and open discussion and open me. So it means if you need to ask questions, you know, I'm not going to give you the result, but you can ask questions. So the idea is really to go over the material to make sure everything is digested and to talk to each other and to do collaborative learning with your peers. So if you find that annoying, don't wait for the end of the semester to complain that this professor gives too many pop quizzes. That was so annoying. Okay, you can always sign to another class without pop quizzes at the end of each lecture. Okay, so Thursday we will have a pop quiz based on whatever we're going to cover today. So today is just slow. We're going to talk about history, and I will introduce, you know, concepts that we will cover in class. Don't be shy, okay? There is no stupid question. I will never make fun of you. Don't hesitate to ask questions, okay? To interrupt me. And it's a good training also for public speaking. Like if you ask questions, if you participate, and I can remember your name, which will be challenging because it's like 80 something of you, then I will boost your grade up, okay? If you participate and if I remember your name. So you want to make sure that I remember your name. At the end, it will stick. What else? So pop quiz here is 12%. Attendance is 5%. So if you miss 1 or 2, it's fine. You have to take attendance on the screen here. You click on your name. And if you are good at math and you add everything up here, do you get 100? If you add all those numbers here, no, you get 105. So it means that you get 5-point bonus. Okay? So it means that if you all get 5-point bonus because when you sum up everything, it's 105. Is that clear? Okay. So I'm not going to fail you if you don't attend the lectures, but I highly recommend that you do attend because just for first of all, you have access to me, so you can ask questions after the class or before the class. So office hours, I am available before the class in AC1387 from I should be here 1 p.m. from 1 p.m. to 2 p.m. or you shoot me an email to make sure. I'm also available after the class, but I know some of you have to run to the bus. Why did I say you that? I forgot. Yes, it's important that you attend the class. Okay. Especially for the pop quizzes. So the pop quiz is online in Canvas. So for example, if you miss the class for whatever reason, you can still take the pop quiz online from wherever you are. Not that you want to miss the class, of course. Is that clear? Okay. So then you go Canvas, very important here. So you go to modules. Okay, so let's keep this. And here you have the important links. So first link here, it takes you to my Dropbox. And in my Dropbox here, you will find all the slides. So you have different folder. Here it says slides, lectures. Okay, so right now you can download the first slides here, unit 1. Okay, I don't get monetized by Dropbox. Okay, it's just that Canvas does not let me upload my slides anymore for whatever reason. So I found a loophole. That's why I'm using Dropbox. You don't need to sign up for Dropbox. Just ignore whatever they say. And another folder here will be tutorials for the assignments. So these are videos. So we'll start with assignment 4. For some assignment 1, 2, 3, I will give you hints included in the assignment. You just want to hide the hints, okay? For the first attempt. In addition to that, you have another folder here with more videos, tutorials, where I go over the problems that you find in my slides. Okay, so in my slides, you're going to have some problems here. So sometimes I'm off by 1 or 2 slides, but you should be able to find the problem. So if it's a challenge for you, I take you step by step through the problems and that are included in my slides. Is that clear? Okay, so that's for Dropbox. Okay, let's go back so you can download it even now. And then here you have a link to my YouTube channel. Okay, so again, I don't get monetized. This is just to help students out. I don't have enough subscribers. I will think I will never have enough subscribers to get monetized. And so this is from last semester, I mean from last year, okay? So you don't want to look at those because, you know, I change year to year. But the next video, that means today video will be uploaded here. So that's for students who miss the class or students who want to go over the lecture again, especially computations, for example, who are too shy to ask questions. So everything is up there. Is that clear? Okay, so it's a YouTube channel just for you. Okay, so what else? Here you have useful links. Okay, so about the textbook. So this is a textbook recommended by the department. So it means that if you have a grant for textbook, you can get the textbook here. Maybe you will get it for free if you have a grant, I don't know, from the bookstore. So that book will be fine. Otherwise, if you are preparing the MCAT or you are in biology, for example, I recommend that textbook here. Okay, it's called Johnson and Cutnell Physics. but you don't need the last edition. You can get a very old edition. Okay, it's the same physics since the 19th century. So even if you get a 20 years old textbook, it will be same physics, same solved problems. Is that clear? So I don't require to buy the textbook if money is an issue. If money is not an issue, so yes, of course, you want to support FIU and you want to support the publisher, you can get it from the bookstore. Otherwise, you can get this one, okay? You can rent it as a PDF or you can buy it very cheap. In addition to that, so I don't do my assignment. I don't use mastering physics. I make my own assignment. Otherwise, you have a free textbook here. It's online. Okay, I cannot do online textbook. I need something paper. That's because I'm older. But if you can do things online, then here it's free. Here you have the PDF version. And you also have tutorials, okay, that goes with that book. Okay, that's students who gave me that link last semester. Here you have another free textbook, another free textbook. Here you have tutorials from Khan Academy. Khan Academy has a lot of tutorials to review the MCAT, if this is the case. In my YouTube channel, because we never have time to cover fluid, and fluid is a big thing in the MCAT. So in my YouTube channel, you will find a playlist covering optics for those who need that, who goes into a medical school, for example, or another branch where you need optics. And I have not optics, what did I say? Fluid. So I have a playlist for fluid and a playlist for optics. If you need extra material, not for this semester, just if you have to take the MCAT. And here you have more tutorials. Is that clear? Any question? So optics and fluid, it's big for the MCAT, and you will find a playlist in my YouTube channel. And again, I don't get monetized, unfortunately. So equation sheet here, very important. So tonight, at the library, for example, you want to print it out. Okay, you need to print out this equation sheet. I don't remember if it was the same as last semester, I'm not sure, but for the test, you will be able to bring it. Okay, you bring it. So you have to print it out and then you can bring it for the test. And you have to get familiar with all the equations you can find here. So if you don't find an equation that you think is useful, you just have to memorize it. So when you're going to bring the equation sheet for the test, don't take any note on it. Okay, is that clear? So this is a very nice equation sheet. And here you see you have some constants, could be useful for chemistry as well. You see you have the mass of a proton, the mass of an electron. So what do you think? Which one has more mass, the electron or the proton? The proton, right? So here we have 10 to the negative 27, 10 to the negative 31st. So this one has a lower mass, 1,000 times less mass than the proton. So that's why in the periodic table, we only take in account the number of protons and the number of neutrons. Okay, we neglect the electrons because they have such a small mass, 1,000 or 2,000 times less. Okay, you see that the neutron has about the same mass, even though it's slightly more massive than the proton. Okay, so we're going to use that. Here, we're going to talk a lot in Unit 2 about charges. Okay, so here you have the charge of an electron, and the unit is the coulomb. Okay, it's a fundamental charge. So it means that any charge, so if let's say you take a balloon, a party balloon, you rub it against your hair, you know it's going to be charged negatively. So you're going to have some electrons here. The charge that you will get here will be equals to integer number of this charge here. It just means that you can have 1 electron, 2 electron, 3 electron, 1 million electron, but you cannot have 1.5. Okay, it's a whole electron. So that will be the charge of an electron. Meter per second, it will be the unit of speed. It's the speed of light. Okay, it's a big number. Okay, the light goes 186,000 miles per second, so it's pretty quick. Universal gravitational constant, that was for last semester. And for example, here, we're going to work with this constant here. You see, it's a big constant, it's the electric constant. So 10 to the 9, and gravity, we had 10 to the negative 11. So what do you think? Which one is larger, the electric force or gravity? Between 10 to the negative 11 and 10 to the 9. Which one is larger? 10 to the 9. When it's a negative 11, it means 0.00000000001. It's a very small number. So it means that the electric force is very, 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 very strong if you compare that to gravity. So that's why my arms don't fall down, right? Because gravity is pulling on them, but you have the electric force that is holding you together. The electric force is what is binding all the molecules together and you don't fall apart, right? So the electric force is very important because it will be involved in chemistry, any chemical reaction. It's about electrons being transferred. It's involved into at the cell scale, okay, the human cell, living cell, all about electrons. DNA, for example, the way DNA is put together, it's through the electric force, and so forth and so on. So even if you're not interested in physics, this semester, electricity is very important to understand. Here you have the magnetic constant, so we're going to learn about magnetism as well. And here it's nice, you have all the units. You see, Coulomb is the unit for charge. Okay, Watt is the unit for power. Very good. Energy per second. If you say your name, I will remember. It's Amanda, right? And it's just because I don't have the right glasses to see. I have glasses to read, but right now everyone is very fuzzy. So you have to remind me your name. Then here, very useful also, kilo is 10 to the third, centi 10 to the negative 2. Okay, and what else do we have here? So electricity and magnetism, that's the equations that you need. And at the end, you have some geometry. Remember cosine, sine, tangent, and so forth and so on. Okay? Conclusion, you need to print out this equation sheet. Any question? So then I'm trying to be organized, which is very hard for me. So you have all the units here that we're going to try to cover. And we're going to start with unit 1. So I'm not going to start with electrostatics. I'm going to start with electric circuits because it's more hands-on. Okay, electrostatic is more abstract, so I keep that for unit 2. And you see here, unit 1, you already have the first assignment. I need to change it. I will upload it probably on Friday. And it will be due next week on Wednesday or Tuesday. I will see. So for the assignment, if you need an extension, you just email me. Okay, I will give you extension as long as the deadline is passed, but don't push it too much. Okay, like don't wait for 1 month after and say, oh, by the way, I forgot to do assignment 1. But if you need an extension, no problem, I will give you extension. And here you have a pop quiz already for Thursday. And it will open at Forgot. 3:30, right? Because no, yes, the class ends at 3:40, so it will open at 3:30. It's like a few questions, just 10 minutes pop quiz. Is that clear? So if you're not happy about the pop quiz, you know what you can do. Any questions so far? I'm trying to remember everything I have to tell you. So the book is not required, but again, if you are taking the MCAT or thinking of going into a medical field or biology or whatever, this is a very nice book. Okay, don't get the last edition because it's more expensive, but older edition is fine. Okay, so I just want to go over a few historical facts and I will introduce the concept that we're going to cover. So starting with electrostatics, you see the electron, electricity, electron. Actually, it comes from the word amber, and amber is a Greek word. And I mean, electron is a Greek word for amber. And maybe you know what amber is, right? It comes from the a tree sap, exactly, a tree sap. And you are too young, but they used to have a movie. There was a movie, Jurassic Park, and it was all about finding, I don't know, they found a mosquito inside a piece of amber and they extracted to the DNA and whatever they did with it. Okay, so this is amber. So the ancient Greek found out that if you take a piece of amber and a piece of wool and you rub it against each other, okay, so what are you doing? You are doing a force over a distance, right? You apply a force over a distance. And from physics 1, let's review. When you apply a force over a distance, you are doing work. Very good, okay? So energy. And this energy is used to transfer electrons from the fur to the amber. Okay, that was not understood at the time. All they understood is that when they are doing it, they could make spark, they could shock. Okay, shock a little bit, especially frogs. I don't know what they had against frogs, but women at the time, they were not allowed to go outside to have a, they had to stay inside. So they were bored, I guess. So they will make those jewels made of amber and they will go around rubbing against their clothes and shocking poor frogs, okay, who will hope in despair. So they did not understand the phenomenon, but they understood that if you rub two, so what do you think are these? Are they insulator or conductor? Are they conductor? Do you think if you take a piece of fur or my hair and you apply a voltage, I'm going to have electricity flowing? No, so they are insulators, right? So it means even though they are insulator, so even though they cannot be part of a circuit, okay, so if you apply a voltage, electricity will not flow. However, you can still, because you are doing work, you can still transfer electrons from one to the other one. So you might ask, why is it that amber will become negatively charged? It's just something that you learn from chemistry. It's about affinity. So it means amber here has more affinity for electrons than fur. Okay? So if the fur loses electrons, that means it becomes positively charged, right? When you learned in chemistry about ions, if something loses electron, like magnesium plus plus, something like this, um, it becomes positively charged. So one thing you always have to remember, only electrons can move. The positive charges are locked inside the nucleus and they do not move. So if you have a charged object, either an electron was lost, so it becomes positive, or an electron was gained, right? And if you take a chemistry class, you understand that everything is about electrons. So for example, if you take oxidoreduction, you know about oxidoreduction, right? That two equations, I never remember oxidant? Is it taking electron or giving out electron? One or the other. So oxidation, it's a transfer of electrons. So anyway, I'm trying to connect to chemistry. So anyway, so that's what they found out at the time, and that's what we call static electricity. Why is it called static electricity? Because electrons, they cannot move. Once they are placed here, they are not going to spread out. They just stay wherever you place them, okay? So it's static. They are not moving. When you talk about current, electric current, that means it's flowing. Static electricity means electrons cannot flow. Is that clear? And then we come to the 17th century, and again, people were bored, especially in the French salon, with the nobles and the wealthy people. You know, they didn't have to work, so they got bored. And at the time, they built what we call the huge static machine, electrostatic machine. So same idea like the amber and the fur, except now it's huge. So you have, for example, a huge sulfur ball, so it's an insulator, and you crank it, so you have to do work. That work is used to transfer electrons from whatever material is here, maybe it's wool, to the ball. So the ball becomes negatively charged, this is positively charged. And then here you have accumulation of charge. So electrons are not happy to be with each other, okay? They hate each other. So the first thing they want, electrons, they want to go back to the ground. They want to find a path to the ground because the ground has a huge reservoir of positive charge and negative charge. Okay, so that's why if you rub your feet against the carpet, for example, you're going to build up charge. And if you touch someone, that someone will feel a shock because the electron will jump to that person to find a path to the ground. Or you will get a shock if you touch the doorknob. Okay, is that clear? So they build those huge static machines, and if you bring now a conductor, like a spherical metallic sphere, so a metallic sphere, which is a conductor, you bring close to it, the electrons here zoom, will jump on it, right? And you make a spark, like a tiny lightning. And because that way they can spread out from each other as much as possible. So they had fun. So they built those huge machine. So you crank again. So positive goes on one side, negative go in the other side. So they will take a cobaye, a guinea pig, like this little boy, hanging the boy on the ceiling. So it's a famous picture of the time. So the shoes here were rubbing against the machine, pick up electrons. So let me ask you, is the boy a conductor or insulator? Will be you okay if I ask you to put your fingers in the plug? No, that's because you are a conductor, right? We are juicy. We are 80% electrolyte. It's the electrolyte that make the conduction, right? So the electron, are they going to stay here or they say, ooh, a conductor, I'm going to spread out, right? So that's what they're going to do. They don't stay here like for the amber. They will spread out and then try to find a way to the ground. So that's how you're going to make a spark here. Okay, so I have a funny simulation from Saturday Night Fever. So you see he's rubbing his feet. The electrons don't stay here, they're gonna move. And usually they have to move outside on the outmost, like on the outside here, they don't stay. They repel each other. They try to move on the outside. Okay, once it reaches equilibrium, you see, most of the electrons are on the outside. So electrons don't like to be inside the conductor, they always move outside. So that's why if you are driving and there is lightning and the lightning is striking your car, as long as you stay inside your car, you'll be fine. Because electrons cannot go inside. Now, if you step out and touch your car, then you might be in trouble. And you see here, you see all those electrons found a way to the ground. Okay? So why do you have some kind of spark? Air usually is an insulator, but if you force it, like if you have a very high voltage, then you have a breakdown of the air, right? An electron can move. Is that clear? So so they start to build all those machines, and they found some use for it, okay, like therapeutic. Like even today we use electricity for therapeutic goal. That's what they did. And maybe they will put things like this and supposed to cure a headache. So they were trying, they were experimenting at the time. Okay, then another breakthrough, 18th century. So when they started to play with those machines, it's a discovery that happened by chance. Okay, so many times in science, things happen by chance, and it was the ancestor of the capacitor. So I don't know if you know what a capacitor is. It's an electronic component that you will find everywhere in any electronics device. And its purpose here is to hold charge. Can hold charge for a very long time until you have a discharge. And the best example I can think of is the defibrillator, since many of you consider going into medical field, for example. Defibrillator here is you have two electrodes. One is charged positively, the other one is charged negatively, and they can hold the charge for a very, very long time because in between them you have air, so the voltage is not large enough, it's 100 volt. But once you put it across your heart, here the heart is at left, I think, left side. So you put it across your heart, discharge it, all those charge combine together, the plus or the minus, and a huge amount of energy is burnt out. Okay, so huge amount of current. The heart is an electric system, so it's going to contract, and you just hope that it will work properly after that. So this defibrillator is actually a capacitor. And the ancestor of the capacitor is what we call the Leyden jar. So it was found 1745, and I cannot say his name. So if you are from Holland, maybe you say it properly. I cannot say it. And I don't think that many people can say it because they name his invention the Leyden jar because he was from Leyden. They didn't call it the Muchenbroek jar. Unless maybe you know a little bit of Holland, from Holland, so you can say it properly, but I don't. So anyway, he was playing with a static machine like this. So this was positively charged, okay? It was a jar with water. So this is positive. What do you think is going to happen when he's holding the jar? Positive attract negative, very good. And where did that negative comes from? From the ground. Remember, the ground is a reservoir for any charges, right? Positive here. Electrons say, yeah, positive charge. Let's go party here. Oh, no. Oh, we can't combine here because you have an insulator between them, right? You have water. So they stay here, positive, negative, and they cannot combine together, except when you touch it here. So then you have a discharge. And then he was shocked and he said, okay, I will never do that again. Okay, so this is the ancestor of the capacitor. So it works like a defibrillator. Okay, so it's a way to hold charge for a very long time, energy. So next we have Benjamin Franklin, who ordered. So that was in Europe. So he was in the US. So he ordered Leyden jar and he was playing a lot with them. And then he came with the idea that electricity, this spark here, it's because you have two kind of charges. So he was thinking of it like a fluid. You have positive and negative. And he also understood that only one of them can move. Which one move, the positive or the negative? Negative, right? Only the electrons. But he didn't know that I had 50% to get it right, 50% to get it wrong. He got it wrong. It's fine. Okay, he got the idea. He thought that it was positive charges moving. So here, you can think of that also as a capacitor. You have a cloud. Inside the cloud, you have dust. The dust rub against each other. Okay, so you can have a separation of charge. That will be positive, for example, that will be negative. The ground will be attracted, so that will be positive, that will be negative. It's like a capacitor. And if the voltage is high enough, then you have lightning. So he did that very famous experiment with a kite. I'm sure you all learned about it in school. Has a kite, it has a thread here. The thread was a conductor and a key. And there was a misconception. Sometimes people think that it was lightning here striking the kite. No, he would have been dead if it was the case. It's just that the air was very electric. You can feel the air when it's electric. Like sometimes you even have the hair, going up. So the air was electric, pick up some electricity flew, attracted by the key, found a way to the ground, and he was shocked, but not too much. It was not too bad. Someone else, and you can dig into the history, try it and die. So I forgot to tell you that for this class, if you do small demo on your own, okay, about what we are doing in class, of course, don't do chemistry, then I'll give you extra credit, but don't do this one. I don't want to be responsible. Okay, so Franklin had a 50% chance to get it right and he got it wrong. So if you have a circuit, so we're going to talk about circuit a lot, okay? You have a power supply, you have connecting wires, and you have a load. Load meaning something that will consume that energy. We pretend, because everyone loves Franklin Roosevelt, we pretend that there are positive charges here moving from plus to minus. So we pretend that the electric current is made of positive charges moving from plus to minus, when actually it's the opposite. Okay, it's electrons moving, and the electrons are not really moving, they just push each other out, right? But that's called the conventional current direction from plus to minus. Is that clear? You want to hear a funny story about Franklin Roosevelt? He came to the court in France, right, with the king and the queen and all the people there, and he was very much loved, right? He was a funny man, very well educated, so he made everyone laugh. So when he asked money to the king for the American Revolution, they said yes. They gave him money, say, okay, we'll lend you money and you will give it back to us, right? So he came back to the US, okay, for the American war, independence war. And what happened is that France went bankrupt because they gave a lot of support to the American against the English, because there was some kind of conflict between England and France, right? So France, whenever it was possible to find a way to piece off England, they would do it, right? But unfortunately, they put so much money in helping the American that they went bankruptcy. The people were very upset, and it ended up with the king losing his head. At least Louis XVI, who was the son of the king who gave money to Franklin Roosevelt. So when France asked the US, give back the money we gave you, what do you think they say? No, come get it, okay? You have to cross the Atlantic. So that's for the funny story. So you can learn about the journey of Franklin Roosevelt to France. Okay, next big breakthrough, maybe you learned that in chemistry. It was done by Galvani. Luigi Galvani, who was not French, Luigi, Italian, of course, right? Luigi. He was Italian, and his thing again was to torture frogs. I don't know what's with frogs. People like to torture them. So he was no, he was in anatomy, so he was dissecting frog, and just by chance, so you had dead frog here, and the legs were hanging on a wire. So let's say it was hanging on a iron, a wire made of iron, and he touched the frog at a different place here with a scalpel, and a scalpel made of zinc. So you have two kinds of metal, right? Wire, where the legs were attached here, and then here he touched it with another metal. And all of a sudden, it seems that the frog became alive again. So that means electricity was flowing. And he didn't understood what was going on. What was going on? He made the first battery. Okay, so I will explain that in the coming unit. But basically, if you want to make a battery like this one, like the one I have here, you need two kind of metal. So for example, it could be copper and zinc. In between them, you have some kind of juice, and then you will produce a voltage. Like you can read the voltage here. 6 volts. Okay, so he made the first battery, but he didn't understand what was going on. He thought that it came back to life because of electricity. So that story inspired Mary Shelley. Okay, have you heard of Mary Shelley? She wrote that famous book called Frankenstein. Very good, Frankenstein. And the idea is, because of that experiment, maybe if you have electricity here, if you make a lightning into a dead body, the dead body will come back to life. So that's the whole story about Frankenstein. I recommend this movie. I don't know if you know that movie. It's hilarious. It's by Mel Brooks. It's called Frankenstein Jr. It's a very, very funny movie. Even though it's black and white and it's very old, it's a very funny movie. Because there is a whole thing about Frankenstein. Because he's doing the same experiment, he tried to bring back to life a dead body. But that experiment was done by his uncle, who was named Frankenstein, and he wanted to be differentiated from Frankenstein. And he said, it's not Frankenstein, it's Frankenstein. So it's, I don't know, maybe I'm too old and you are too young, but it's very funny. So just after that, in France, you had Volta. Okay, so you see here 6 volts. It's a unit of measurement for voltage. Okay, so voltage is measured in volt, and volt is named after Volta, Alessandro Volta, who lived in France. Okay, came from Italy, went to France, and he discovered the battery, how to make a battery. Okay, so I'll talk about that in the next unit. But he was knighted by Napoleon, because at the time in France it was Napoleon. After the head of the previous king, then came Napoleon, and he knighted Volta. So that's why he's known as Count Alessandro Volta, and he built the first battery. Okay, so I can tell you even now how it works. Very simple. Okay, so first of all, you see that it's called voltaic pile because pile in French means a pile, a stack. So he understood the experiment done by Galvani. Okay, he understood the physics behind it, and it was a big breakthrough because he built the first battery. So you were able to produce electricity as much as you want, right? It was easier than a Leyden jar. So the idea is that you need 2 types of metal. So for example, you take copper and zinc, and between them you have some kind of juice. So it could be acid, like hydraulic acid, or it could be brine. Brine is like a salty water. Okay, and with that you have a voltage of 1 volt. So that will be one cell. So 1 volt, and then 1 volt. How many volt do you think I get here? 6 volt. Does it make sense? 6 volt, like this one. Okay? So 6 cells will give you 6 volt, and it was a big breakthrough. So this is called batteries in series. And for the demo, you can make a lemon battery or a potato clock. Make a battery from a potato. I will show you how, but it's an idea for an experiment. So talking about series, so I can introduce whatever coming next. Doc. Can you see here? So these are batteries in series. So I don't know if you recognize them, but each one of them is 1.2 volt. Do you see that? And I have 1, 2, 3, 4, 5, 6, 7, 8. Do I have that 1.2 volt? So yes, so 1.2 volt times 8, 9.6. No, what did you say? 1.2 times 8. It's 9.6, right? Is that right? Okay, 9.6 volt. So that's basically what he did with his experiment, stacking up batteries, right? And this is for airsoft, by the way. I took it for my son, thought it was nice. So here you have something also that you use every day. You have 2 AA. Each one of them is 1.5 volt. So what's going to be the voltage? 3 volt, okay? So volt is potential energy. That will be the potential energy you give to each charge that will flow in the circuit that you're going to build. And here you have 6 volt. Again, 6 volt, you have many cells inside to build the 6 volts here. Okay? So it's just an introduction. Here you have his batteries here that he built at the time. You see, it's a stack. Okay, and you keep building up, building up, building up, and now you have a voltage, and you can build a circuit, so you can control electricity for the first time. Before that, you had a Leyden jar capacitor, but you cannot control the amount of electricity that will flow. With that, you can control the voltage, so you can control the electric current and have a circuit. So it was a big, big, big revolution at the time. For some reason, he didn't like Luigi Galvani. I don't know why. He made fun of him. And so when the story is that when Napoleon invaded Italy, he made sure that Luigi Galvani would lose his job um, and didn't have pension. I think he died penniless. I don't know, maybe Volta was trying to defend the frogs or something, but definitively didn't like Galvani. Okay? And then we come to Humphrey Davy. Okay, Humphrey Davy, beginning of the 19th century. So everything happened during the 19th century as far as electricity is concerned. Okay, so it was one breakthrough after another one after another one. So Humphrey Davy, okay, so at the time they were able to build what we call the through battery. Okay, so it looks like a car battery today. And he put all those batteries in series, 2,000 of them. He was able to produce a huge voltage. And if you bring them close to each other, you have a breakdown of the air. So you have a huge spark. That spark was so bright that you could light the street. Okay, so it was the first street lamp. Before that, they used candles or oil lamp. Okay, so it was the first time. So he did that with batteries in series. You have an arc lamp, and the light was very bright. Okay, in addition to that, for those into chemistry, he did something amazing. He used electrolysis. So you know electrolysis, right? You take a battery, okay? You put the 2 electrons in some, for example, in water. So what's going to happen if you put electricity in water? What's the equation, the formula of water? H2O. So if you put electricity in water, plus and minus, you're going to bring energy into it. And that energy is going to be used to break apart water molecules into what? Huh? So no, it could be iron. It will be iron for my next example, but for water, it will be 2 gas, hydrogen and oxygen. Okay, so 1 electrode, you will have hydrogen. I can see that because if you lit a fire, a match, it flammable, and the other side will be oxygen, hydrogen, oxygen. So this is called electrolysis. So he was the first one to use electrolysis to isolate. Then you are right. Potassium, which is an ion, sodium, borium, whatever it says here, calcium, strontium, and magnesium. So big breakthrough. Okay, it was the first time in chemistry they were able to isolate those components using electricity. So big breakthrough. He was also very famous because he was a very good public speaker. He was so good and he will be doing all those experiments that people will wait to listen to him at the Royal Institution of London. Okay, so he was very famous. Interesting also history because he made it from very low class all the way up. And to give those lectures, he will get high. And he will get high on laughing gas. Do you know the laughing gas? Right? What's the equation? Nitrous oxide. Yes. What's your name? Huh? Steven. Tell me your name when you say something. Is that like I can see here first row, but then everything becomes fuzzy. Nitrous oxide, which is NO2. Oxide is O2, no? I don't know my chemistry. I didn't like chemistry at all. Well, it was a disaster for me, chemistry. So NO2. And so you are still using it at the dentist, like if you are for kids, for example, because it makes you euphoric, okay? Very, very happy. So he was using that before lecturing, and he will also organize party where everyone will get high with the laughing gas. So he was very famous for that, okay? Unfortunately for him, he died very young because laughing gas, right? He damaged his yes, right? You die from the laughing gas. It's not a laughing matter, right? We can make a lot of jokes about that. So he damaged his lungs. So don't take laughing gas, except if you go to the dentist and you are very, very sensitive. But I asked once, I went to the dentist, I'm super sensitive. I have a phobia about dentist. And I asked, can I have that? And he said, you have to pay $70 or something like this. So they make you pay if you want to take it. So anyway, so then we came to the end of the 19th century. Okay. And that's when, so if you are interested, I'm not going to go into details because it's more advanced, but if you're interested, this is a great video to watch. It's about particle physics. And if you go to advanced chemistry or nuclear physics or nuclear medicine, I highly recommend to watch this video. It's very easy to watch, and he explained all the discoveries, right? The electron, the proton, the neutron, and so forth and so on. So, but I'm going to go skimming through. So, big breakthrough here by J.J. Thomson. He did an experiment and he discovered the electron. for the first time. Okay, so basically you have some tube here. It's a vacuum tube, so you take the air out and you have a very high voltage. So this is a negative electrode, so a lot of electrons here. But because it gets so hot, electrons, they get excited and they break free, right? So then you accelerate the electron and you can visualize here the beam of electron. And doing experiments, he was able to show that it's a negative particle, and he was able to show the ratio between the charge of an electron and the mass of an electron. So with those two experiments, the electrons was discovered and the mass of an electron was measured and the charge of an electron was measured. Okay, so big breakthrough. So he came up with a new model for the atom. So if you take a chemistry class, usually the first chemistry class, they teach about that. The first model, so the atomic structure was called plum pudding model. Have you heard of plum, plum, plum pudding? Right? Have you heard of it? If England, right? That's what you don't find that here, do you? It's not very good. And anything that comes from England, yeah, right? Do you like English food? No, that's terrible. Like the Jello thing, that jingle, are red or yellow. So anyway, they have those disgusting thing called blood pudding. But the idea, it's like a muffin, a blackberry muffin, right? So his idea was that you have some kind of dough, positive dough, right, with little electrons embedded inside. That was his model. It's improving, right? It was the first step. And then after that, his own student did another experiment, and he shows no, that's not how it works. You actually have a positive nucleus and the electrons around. So improvement. Not quite right. What are we missing inside the nucleus here? The neutrons. You are missing the neutrons. So neutrons are coming next. They were discovered in 1930 something, but it's already something. What's wrong about those electrons here? First thing you learn in chemistry, the electrons have to be on orbitals, right? Yes, orbitals, energy levels, right? They're not supposed to be hanging like wherever they want. So that will be more a better model here. So you see, that will be the Bohr model. In 1932, they do another experiment to find a neutron. So you have the nucleus here, and then the electrons on shell, energy level, right? So that's what you learn in chemistry, right? And let me ask you something. Is this something wrong here? Because you see you have neutron and all positive. Do you think positive charge, so these are protons, do they like each other? No, they repel each other, right? And they still stick to each other. So if we just talk about the electric force, negative and negative repel each other. Okay, so it should break apart, right? So they don't. That's because there is another force called the strong nuclear force that glue all those particles together. But at some point, you have so many positive charges that they cannot be glued together anymore and it break apart. When do you think that happens? Start with a radioactive. Okay, uranium, for example. Uranium is radioactive because it's so big, 92 protons, and you don't have enough neutrons to hold that together. That uranium decide, cannot hold it anymore. And they hate each other out so much, break apart and become something else. Okay, so that's a good model. It's not exactly what's happening because if you take a chemistry class, we talk about orbitals, but that's fine for our class. You see those electrons on the outmost layer, chemistry. How do we call those electrons? valence, huh? You said valence electrons. Okay, those electrons for conductors like copper, they are free. They are free to leave their nuclei. They are not tightly bound to their nuclei. They are free to go around, right? So if you take a chemistry class, I'm sure you did. I'm sure you know more about chemistry. You have to take so many chemistry classes. That will be the structure of a typical metal like copper. It makes like a lattice, and the outmost electrons, they are not faithful. Okay, they will wander around here. Hi, how you doing? Okay, hi, how you doing? Okay, hi, how you doing? So it's like a sea, like a wave, right? They are not attached to their nuclei. And when you apply a voltage like this here, I don't know where is my battery now. So if you apply a voltage, okay, to a conductor, then the electron will start to flow. Okay, otherwise it's free to flow, to wander around. So that's a conductor. Now, if you have an insulator, it's the opposite. They are very faithful to their nuclei and they won't leave it. Okay, they cannot break through. Even if you try to apply a voltage, okay, across, I don't know, a balloon, for example, you are not going to get electricity. Okay, so they are very bound to their nuclei. Is that clear? So just here a little bit, here you have a conductor. Conductor electrons are free to conduct electricity, free to flow. If you apply a voltage, insulator like amber, like plastic, like wool, okay, insulator, the electrons cannot make it, cannot jump here. They are not free to go, to flow. If you apply a voltage, and in between you have semiconductors, okay, and that's another story. Semiconductors was a big revolution. It happened in the 1940s, and that's when they made the first transistor, which is a semiconductor. So a semiconductor will be used as a switch. Okay, so like a switch, you close, electricity flow, you open, electricity cannot flow. So what do you think you can get? Like flow, 1, don't flow, 0, don't flow, 0, 0, 1, 1, 0, 0, 0, 1, 1. It's what you have in your computers, right? It's a digital age. With semiconductors, it was the beginning of those small computers, laptops, smartphone, and all the electronics that we have today. Okay, so we have come a long way from this, okay, before the semiconductors, transistors, to this today. So those here, those machines were huge, as big as this room, and they were not even as powerful as my smartphone today, and very bulky, didn't have keyboard. You have to punch cards 0 1 1 1 0 0 1 1 0 0 1 1. Usually they will hire women because they have the patience, detail oriented, right? 0 0 1 1 0 0. It's just a stereotype, okay? But it's true that they hire women and the men they were here, right? So imagine me having to write all the physics on the blackboard. When I started teaching long time ago, okay, more than 20 years ago, we had those things here, antique. We have to write on the board, even though we didn't have ladder to climb up. So today we have this, just thanks to the physics. Okay? Any question? You have no question? Okay? And so you have two types of charge. You have positive and negative. It's only the electrons that can move. Okay? So either if something is positively charged, it means an electron or electrons were lost. If something is negatively charged, it means electrons were gained. Okay? Another thing is that charge is quantized. It means that you can have 1 electrons, 2 electrons, 10 electrons, but you cannot have 10 and a half. Okay, it's like the electron is like it's a fundamental particle. If you crack it open, as far as we know, there is nothing inside. Okay, if you crack open a proton or a neutron, you have things inside, but not the electron. So that will be the charge of an electron. The unit is the Coulomb, named after Charles Coulomb. Okay, and so it's hard to explain what a charge is. It's a property of matter, like mass. So if I say my mass is 70 kilo, it's just my mass. Okay, so likewise, you can find the charge of objects. So if you take a balloon, for example, and I will do that on Thursday, you rub it against your hair, the balloon will be positively charged. And you can find the amount of charge in Coulomb. Okay? Okay, so next we're gonna start talking about electric circuits. Okay, so I will explain. I went faster than I expected. So do you have any question? Okay, so you're gonna have a pop quiz for next time based on what we have covered. Don't fall asleep. You can you can bring a coffee or something to wake you up if you want. It's hot, no, isn't? It's because maybe it's too warm here. Shall we open? Maybe I'm gonna turn on the light. Okay, so you don't fall asleep. So next time I will bring a demo for you. I didn't bring it today, but I will bring next time. So that will be, we're going to start talking about electric circuit. So for basic electric circuit, first thing you need a battery, for example, or a power supply. Okay, so I don't have to use a battery. I can use this outlet, for example. That will be my power supply. Okay, but you're right. In that case, it's a battery. So what's going on inside the battery? You have a chemical reaction. There is a chemical reaction that will produce energy. So chemical energy will be turned into electrical energy. Okay, so you have this is a source of energy, so we call that the power supply, and that energy will be delivered to what we call the load. Okay, load is the component in an electric circuit that consume energy. So energy is always conserved. So whatever is delivered is going to be consumed. In between them, you need to have connecting wires for electricity to flow. Okay, so if you replace that connecting wire by a piece of wall, is it going to work? No, right? Unless you apply a very high voltage, then the thing will be on fire. But otherwise, you need some kind of metal. Usually, it's you have an insulator around, like rubber. Okay, so people don't shock themselves. And sometimes you have a switch. So the way to understand it is you have to think of a hydraulic system. Okay, so in a hydraulic system, you have a pump. Okay, so that will be the source of energy. And imagine you have water flowing here, but imagine gallon. You see the gallon of water? Okay, so what will be the job of the pump? It's to take each gallon of water and to raise it to what kind of energy? Potential energy. Okay, remember that if you take a mass above the ground, you are doing work. Okay, so this here, that mass here is gaining potential energy. It's potential because I can get back my energy, turn that into kinetic energy. Okay, so each time you have potential energy that you can get back, it's called potential energy. Okay, so each gallon of water is raised to higher level of energy. Okay, so it has potential energy. And then here you have a valve, so it's like a switch. And if you let the water flow, all that energy can be delivered to the load. So in that case, it's a wheel. Okay, so it's going to be kinetic energy. And then you start the process over. Get that? So in an electric circuit, it kind of works the same way. So because we love Benjamin Franklin, we're going to pretend that what is flowing, positive or negative? Negative in reality, but Benjamin Franklin, so we're going to pretend it's positive. It will be easier to understand. Okay, so let's say you have positive charges flowing. Okay, the unit of charge is 1 coulomb. So imagine you have 1 coulomb of charge flowing here. So if your battery is 6 volt, like this, it means, and you have a circuit, I will bring a circuit next time. So you make a circuit, you connect to a load here, and then it comes back here. That means that every coulomb of charge, so 1 coulomb, every coulomb of charge will be raised to the potential energy of 6. What's the unit for energy? Joule, 6 joule. Okay, that's the meaning of your voltage. So for example, if you have a car battery, you sometimes you have to change the car battery. So what's the voltage of a car battery? 12. So that means what? It means that each coulomb of charge leaving the plus to go through the load, like the starter, back to the minus, will be given 12 joule of potential energy. So it works the same way here. We talk about potential energy. So each coulomb of charge will be raised to a higher level of energy, potential energy. That energy will be burnt out, delivered to the load that will consume that energy, and then the coulomb of charges flow back into here. Okay? That's how it works. So let's see, next slide. So here, because everyone is familiar with the battery that you have in your car, that this is 12 volt. So what does it mean? It means you have, can imagine you have this coulomb. So this is 1 coulomb, 1 coulomb, 1 coulomb of charge, holding 12 joule of energy, flowing and delivering the energy to the load, and then they come back. So a battery is able to apply a pressure, right? It's applying a pressure, it gets a boost. So what's going on here? You have some chemical reaction. That's why the battery gets drained at the end, because you have a finite number of energy from chemistry available. Is that clear? Well, that's how it works. So you might ask, okay, I understand 1 coulomb of charge, okay, will be holding 12 joule, get pushed. And then how can I change the number of energy available? So I cannot change the energy per charge, but I can change the number of the volt. Let's say I can change the voltage. That you are right. That's what we did when we put in series. Okay, you can actually, it's a good point, because I don't know if you last time I was taking a walk in. So sometimes I take tangent. Okay, make sure I don't take too much of a tangent. But I don't know what's going on in North Miami, but you find those golf carts. So I don't know I really have no idea what's the deal with this golf cart. But there was one that was broken next to a canal. So I think that people steal it and then they have fun and then they dump it in the canal or whatever they do with it. But it was open, and I thought, oh no, that's interesting. How do we make a golf cart? Oh, it doesn't seem to. How many batteries do you see here? 6. And one battery is how many volts? 12. So altogether, what's going to be the voltage? 30. Okay, 72. 72, right? 12 times 6, right? Sometimes I space out, I have to come back. 72 volts. So 72 volts means that each coulomb of charge will be given how much energy? 72 joules, right? And that's what they do. So I read that you can even order like a truck, mini truck, and order from China, and then you can build that yourself. You just need the batteries and a little bit of connecting wires. Doesn't seem too hard to do, kind of. So anyway, I took the picture. So, but let's say you cannot change the voltage, but you want to change the amount of energy delivered to the load. What is it that can be changed as well every second? Each coulomb of charge has 12 joule. So what is it that you can change every second? Yes. Who said that? What's your name? Louisa. Yes, you are right. The number of coulombs. So for example, every second, if you have 4 coulombs and each coulomb is holding 12 joule, how much energy will be available? 48, right? 48, 4 times 12 is 48 joule. Okay, so the amount of energy delivered per second depends on 2 things. The voltage, so that means the joule per coulomb, and the number of coulombs per second. Is that clear? Make sense? So you can control the amount of energy delivered per second. And remember from physics 1, now I can see everyone. From physics 1, what is the definition of energy per second? Consumed or delivered. In physics, we call that the power, Christina, power, right? It's the power. So we can control that. If we have a given voltage, we can change the number of charges. So you know what is it called, the number of charges per second? What are we missing? We talk about power, we talk about voltage. What else we can talk about? The current, right? The current is actually the number of charges delivered per second. Okay, so we're going to go in more details, don't worry, but the current is a physical quantity. The unit is amps. Okay, and by definition, the current is the number of coulombs burnt out by the power supply per second. So in a typical house, usually you can go up to 20 amps. Okay, so 20 coulombs per second that you can drain from the power supply. You don't want to go over 20 amps, because what's going to happen if you go over 20 amps, the fuse will open, will break, because you don't want to start a fire. It happened a lot at the beginning, when they didn't have the fuse. You will start a fire like that if you start to drain too much current. Okay? Is that clear? So that's the basics of an electric circuit, and I will bring one next time. Let's see, I can have a simulation to change my glasses. Oh, how many amps do we have now if you have 4 charges per second? 4 amps, right? Amps will be the number of charges, the number of coulomb per second. So that will be the amps. The voltage is the energy per charge. And you can control the amount of charges using what is called a resistor, but I will leave that for next time. But you can see here, I have a nice picture. Here. You see those little coulomb flowing. And here you can have like a gnome or someone counting 1, 2, 3 every second passes through. That will be 3 amps. Okay? If you increase the number of amps, you increase the number of charges, you're going to increase the energy delivered. Okay? So let's see. Next time I will bring. Oh, I just want to show you like something you are familiar with. So this is a car battery, and how many volt? 12 volt for a car battery. And you see, usually when you have a circuit, you have to close the circuit. But inside the car, you close the circuit with the car itself, with the chassis, right? So that current from your car battery will be used for the starter. So starter is what will start the wheel, okay, because the wheel has inertia. So you want to start it, okay, otherwise you won't start on its own. The current will provide current to the plug to ignite and to lightning, for example. Okay, let's see. Let's build one circuit. Any question? Don't hesitate. So, okay, so I want to build a circuit. So what do I need? A battery, very good. That will be my power supply. Okay. And a switch, okay, I agree. Let's take a switch. And then a wire. Oh, you don't want to put a load? Let's see what's going to happen if you don't put a load. Interesting. If you don't put a load, let's see what's going to happen to my circuit. So 9-volt battery. Wow. You know what is it called? It's called a short. It's called a short, right? Because there is no load to consume the energy. So that's what happens if you plug your fingers into the outlet. That's going to be a short circuit, and that's very bad. Okay, so you don't want to do a short. That's what you do. Like when you can start a fire with a 9-volt battery. Like if you have a 9-volt battery into your drawer, and then maybe you have some metallic thing that connect the plus and the minus. It gets very hot. You can start a fire. So instead, what do we want? A load, right? We need a load. Okay? So imagine this is the conventional current. Okay? So imagine this is 1 coulomb of charge, little arrow here. Each little arrow is 1 coulomb of charge. Each coulomb of charge will have how much energy? 9 joule. Very good. Okay? And that will be delivered to the load, and then they come back without energy to the battery, and then they get a boost again. Is that clear? So I can measure the current. The current will be, you see, how many charges flow through this every second, okay? Or how many charges, how many coulombs are produced by the power supply. So if I, for example, if I increase here, okay, do you see how by increasing the voltage, okay, it's like the rate at which is flowing is increasing. That means that every second I'm going to have 6 coulombs of charge going through. I have 6 coulombs of charge produced by the battery. Do you understand? Okay, so that will be amps. What is the amps? It's the number of coulomb of charge, the number of coulombs produced every second by the power supply. So that's what we call the electric current. and then you can have a voltmeter to measure the voltage. So when you are measuring voltage, it's like measuring height. Okay, how much potential energy is available? What's the height? So in that case, 60 volt will be how many joules per coulomb? 60 joule. Okay, so you have 60 joule per coulomb, and then you have 6 amps. Okay? So sometimes you see it's you can think of current as a measure of how fast the coulombs are flowing. Are you with me? So sometimes you think, oh, it's too much current. You want to slow them down. And we're going to see later that in that case, you use something called a resistance, right? And you see now it's 3 amps. Okay? So that component here, it's called a resistor or resistance. And its role is to decrease the amount of charges flowing every second. So it's not as bright. Is that clear? So it's an introduction. We'll go more into details. What do you think is going to happen if I increase the resistance here? It's going to slow down. Very good. It's going to slow down. You see? And because it's slowing down, you don't get as much energy per second, so it's not as bright. So if you have a hydraulic system, it's like you are able to make the pipes narrow, right? More, you squeeze the pipe. That's what you are doing. So you decrease the current. So if you have like a battery in a car battery, you're going to have about 100 amps. It's a lot. But if you touch the electrodes, you should be okay because in your hands have a lot of resistance unless you wet them. So that will be bad. But if you have dry hand, you put so much resistance that the current will have a very hard time to flow through you. It will, but you won't have that 100 amps. However, if you take a car battery, so dangerous to do, not that dangerous, but you have to be very careful. And if you take a weight, like a piece of metal, like a wedge, right? Like what you use as a tool, and you put them across the electrodes of your car battery, what's going to happen? You make a short, and it will stick. You won't be able to take it back. It will melt. Okay, because you make a short and there is no resistance. 100 amps is enough to melt the piece of metal, and it will stick to it. Okay, you won't be able to take it back, and your battery will be drained. Okay, so not to do it. Mm-hmm. You said for the car battery, it gets worse if you have water. Yes, I mean, if you were to touch like this, like I'm doing it, see, I'm not afraid. You see, I cannot feel anything. I would if I put a connecting wire, then I will make a short. This is a short, but my skin has such a large resistance that very little current flow through my finger and I don't feel anything. So if you do the same thing with a car battery, you should be okay. So don't do it, but you should be okay. Okay? But if you wet your hands, then you decrease the resistance and you won't be okay. It's very good because water decreases the resistance rate. What's your name? Joanna. Joanna, yes. Right? Well, I'm going to stop soon, but for the little story, in France, I don't know if you know him, our Elvis Presley was called Claude François. He was a very, very, very famous singer. Okay, he was like a rock star. And he had a problem with like what it's called OCD, like he liked things to be perfectly right. And he was in his bathtub, okay, and so his feet were wet, and he didn't like the way the light bulb was set, so he touched the light bulb to fix it, and guess what happened to him? He died, okay, electrocution. He was very young. Claude François, you can Google his story. Conclusion. don't go and play with outlets if your hands, especially if your hands or feet are wet, because it will decrease the resistance you write.